Hey everybody, welcome back. We're going to get started with a refresh your understanding poll. You can go to Ed and to see all of the polls for today. Just remember to log in first so that we can log it for participation points. The two questions ask you to think about what we talked about last time in terms of Markov decision processes and what sort of guarantees or type of properties they have. Yeah.
Could you re-explain what is a tabular MDP again?
Yeah, great question. Tabular MDP is where we can write down what the value is of a state as a table. So like you can just have one entry for what the value is for each state. This is in contrast to like neural networks or things like that where you don't have one parameter per state. Okay, we'll take like another 1 or 2 minutes. We have a good amount of controversy on these questions, so I'll see how this converges.
I remember seeing this a to the power s number in a previous context. Was it in the context of policy iteration or what was it?
Yeah, does someone want to remember why is a to the s important? I remember why it is. Yeah, remember your name.
Is it like the number of total possible policies?
That's exactly right. What's exactly right? So there's at most a to the s potential deterministic policies. All right, so most people selected the correct answer for the first one, which is this is true. So asymptotically, this will value iteration and policy iteration are correct in the tabular discrete Markov decision process case, and they will asymptotically both converge and compute the right value function. The second one looks like it's pretty evenly split, so I'd like you to turn to someone near you and argue for what you said for the second one.
So what you said, right? Like in value iteration, each step can increase the value.
All right, so maybe re-vote if your answer has changed. Might not have. So the answer is true. And about half of you said that. Does someone want to tell me why this is true? Yeah, is it? Yeah.
I'm not sure if this is correct, but I think that value iteration might not be guaranteed to converge. So if it's not guaranteed to converge, it could just be unbounded.
So that certainly would be the case, but fortunately it is guaranteed to converge if gamma is less than 1. But you're correct that it can require more iterations. Does anybody have anything? And remember your name.
So my thinking was that in policy iteration, in each step we're going to improve to a new policy, but in each value step you might not reach a new policy. You might take multiple steps to reach a new policy.
That's right. So in policy iteration, and I talked to some people about this too, there can only be a to the s. So in policy iteration, there's at most a to the s because you only go through each policy once. But for value iteration, it can be more. And I'll give you an example. So one way I would think in general, if you see this sort of question, is to think about, well, can I come up with a counterexample to say where this would be different? So consider a really silly Markov decision process where there's just one state and one action. So if there's one state and one action, there's literally one policy. You can only do one thing, and there's only one state to do it in. So that means that policy iteration is going to take one round. But for what value iteration is going to do is it's going to keep going until the value function stops changing, or stops changing within like a very small amount. And so what would happen in value iteration, and feel free to go back to your notes from last time, is we would start off, and let's say the reward is 1 and gamma is 0.9, and we initialize the value function to 0. So then if you use a geometric series, and if you haven't seen that before, just come chat with me about it. I'm happy to say the V star of this state is 1 over 1 minus gamma, because you get 1 plus gamma times 1 plus gamma squared times 1, ... So, because it's like you're always staying in that state and you're always taking that action, and you just day in and day out, that's what you get forever. So the actual value function that you get eventually is 1 over 1 minus gamma. Or about 10. But after the first iteration of value iteration, V1 of S is just 1. So that means, 1 is not close to 10, or not that close to 10, so we haven't converged yet. So we'll have to continue to do a bunch of iterations of value iteration. Whereas at that point, policy iteration would stop, because it would just evaluate the value of the one policy we have, which is to take that one action, and you'd be done. And I bring this up just to illustrate that even though both of those algorithms are guaranteed to converge to the right thing, eventually they can have quite different behavior in the short term. Did you have a question?
I was just going to ask, is it only converging in the limit? Or?
All of them are only converging in the limit. Yeah, so all of them are converging asymptotically as you do this over and over again. Good question. Great, well, welcome back. If you just came in, feel free to go through the questions later. What we're going to be doing today is to kind of continue in this more simple setting where we don't do any function approximation, but we are now going to think about the fact where we don't have models of the world. And what I mean by that is that we're not given a dynamics model, and we're not given a reward model. Our agent just has to try things out in the world to learn how good they are. And we're going to start with model-free policy evaluation. In the case where we still have a small enough number of contexts or states that we could write down a value for every single one of them separately. So that's why we call it tabular. I'll just say one thing in terms of logistics. So office hours are on the website. We'll try to keep that calendar updated. It's just a Google Calendar. It'll include the location. And if you go to queue status for the one-on-one office hours, we'll make sure that the Zoom is either on that or on the website. I'll have office hours starting this week on Thursdays, and mine are for project and conceptual questions. So feel free to come ask me about anything in class. I won't be going through code, but you can go talk to the TAs about that. Or you can come in and brainstorm about projects or general questions about reinforcement learning. I'm sure some of you are starting to think about projects. Just in general, some people are asking sort of what's kind of in scope. I put something on Ed about that, but also in general, it can be like a new idea for reinforcement learning, a new application. It can be something you're doing if you're already doing research in reinforcement learning. It can also be replicating part of an existing paper. And this is really helpful, actually. It's helpful for the whole community because there's a lot of work going on. And people are making different choices about hyperparameters and seeds and things like that. So it really is very valuable, too, to see what things we can replicate. Does anybody have any questions about that or other logistics of the class before we get going? All right, so let's get into policy evaluation. So as I said, what we're going to be doing today is to think about how do we learn through direct experience how good decisions are. And we're going to assume that we have a fixed policy. So again, like our boss says, how good is this way of, advertising to customers? Or maybe you're in a setting where you're trying to see how good is the patient outcomes from the current protocol. And the idea is that we're only going to be using data from the environment. So, and today this experience is going to come from executing that policy. Let me just move this up so you can see a bit better. Today we're going to assume that when we get this data, it's from directly executing a particular policy. Later we'll talk about other sort of relaxations to this. And so I'm going to try to motivate today why this is a useful thing to do and what sort of properties we would want to try to compare different algorithms. So it will turn out that this type of thing comes up all the time. It comes up when we actually want to make decisions and learn better policies. And it's going to be an important part of much more complicated algorithms like deep Q-learning and policy gradient and other things, where we want to sort of be able to see how good are current things so that then we can take gradient steps or improve our policy. Okay. So this is what we're going to try to cover today. We're going to cover Monte Carlo policy evaluation, temporal difference learning, certainty equivalence, and batch policy evaluation. And maybe raise your hand if you've seen temporal difference learning before. Okay, raise your hand if you've seen Q-learning. Okay, great. Q-learning is the control version, basically, of temporal difference learning. So you'll see a lot of similarities there. Okay. All right, before we dive into this, I just want to recall a couple definitions we'll have. We're going to use G for the return, which means that from this particular state, what is the discounted sum of rewards we get for a particular episode? The state value function is saying, on average, what is that reward we get? And the state action value says, if I start in this state, take this action, and then follow this policy, what is the expected discounted sum of rewards? So we saw last week that we might want to do dynamic programming for policy evaluation when we do have access to the models. So again, what I mean by that is that where someone gives you a function for the reward and a function for the dynamics model. And so we saw we could do this sort of Bellman-like backup for a particular policy. This was different than the Bellman equation because there's no max. We're not trying to take a max over different actions. We're just taking whatever action is specified by the policy. And in this equation here, this is for like a deterministic policy. Otherwise, we need some additional averaging over all the actions that could be taken by that policy. And just to remind ourselves here, before we converge, this policy, this V pi k, is like an estimate of the value of the policy. It's not the actual value yet. It's just like an estimate, and it's hopefully improving over as we do more iterations. And another just good thing to remind ourselves of is that this is here, this sort of expected discounted sum of rewards. What we're doing in this equation is we are plugging in this term as an estimate of the expected discounted rewards for the future. So we're saying like, oh, we've got this estimate of the value function. We're going to plug in and say my reward is my immediate reward plus my discounted sum of future rewards. And this is what I'm using for my discounted sum of future rewards. And so this is known as bootstrapping because we're plugging in one estimate in order to help us do another estimate. And we'll see a picture of this graphically later. All right, Monte Carlo policy evaluation is a really simple idea, but it's very useful and it is commonly done. So essentially the idea with Monte Carlo policy evaluation is we are just going to simulate or act in the real world. So this is just saying you've got a policy, which means you know what action to take in every state. Today we'll mostly focus on deterministic policies just to make it easier. So I'll just say that for most of today, assume pi is deterministic. But all of these ideas can easily be extended. It's just easier to write that down without having to do an expectation over actions everywhere. Okay, so what's the idea in this case? Well, the value function is just an average over the returns. like an expectation over the trajectories or the returns you could get by following the policy. And therefore, the value is just the mean of returns. And we know how to approximate means. We just do things a bunch of times and we average. And so as an example of this, it might be something where someone says, okay, when I want to know if we, say, give a particular set of patient treatments, and maybe those treatments take a year, for example, and someone wants to know, on average, how good is that? Well, what you could do is you could have 100 patients all go through that particular protocol for a year, and then average their outcomes. And that would be an example of Monte Carlo policy evaluation, is you just execute the policy for many different episodes, and then you average. Okay. And one thing just to note here is that you can have cases here where not all the trajectories are the same length. So imagine in the patient case I just gave, you might have that some people drop out of a trial during the year, or maybe they finish their treatment successfully, and so then they're also done. So all the trajectories may not be the same length, but essentially you can just think of it as just have many, many trajectories. Maybe this one has a G equals 10, this had a G equals 5, this has a G equals 10, and you just average over all of them. And that is your value function. Okay. Now, one of the benefits of this is that when we do this, we're not actually, benefits or drawbacks, and we'll talk about this. This is making no assumption that the system is a Markov decision process. It's just averaging. So your system might not be Markov. And what I mean by that is that you, in general, will have a finite set of features to describe the state. So if we think about that patient example I just had, maybe you have different vitals of the patient, maybe you have static demographic variables, but we do not have all the features that are probably going to describe how someone's going to react to a set of treatments. And so because of that, you may or may not think that in the features you have access to, the system is Markov. But this doesn't require the state to be Markov. It's just averaging. You just roll out your policy many times and you average. Now, a really important thing here is that it can only be applied to episodic MDPs. So what do I mean by that? I mean, your episode has to end in order for you to see what the total return was. So if you have sort of horizon lengths or episodes that last for a year, that's okay. It's a little bit slow, but you could do that. But if you want to just think of how good a policy is, if you just are going to act forever and never stop, this wouldn't work. Or not without some additional approximations. Does anybody have any questions about either of these two things, about it not assuming the state is Markov? Yeah.
We were talking about like medical treatments.
Yeah.
So, does this only work if like the treatment only lasts like the same amount of time for every patient, like 6 months? Because they have different lengths, right? Like how can that be episodic?
Great question. Yeah. So what is like, well, can it be episodic if the episodes are different length? It could be. So it could be that you have like a fixed policy, and maybe that policy says if someone doesn't respond to this type of treatment, we do this additional type of treatment. And in fact, that's very common. As long as the episode is guaranteed to end, like that the treatment could only last, say, for a year total, you can still average over all those outcomes. You just sum over the return for those different ones. Yeah.
For each of these trajectories, are we supposed to begin with this like different state, or we can actually start with the same state?
Great question. So if we want to get a value function for all states, we need to see all the states inside of these trajectories. And we'll talk about how we estimate these in a second. So I think this will be answered. Okay, so for example, how might we compute this? So we would like to get the value for all the states that are reachable inside of your policy. So what you could do is we can initialize two different variables. One, N of S, is just going to be the counts of the number of times that we've updated our estimate for state S. G of S here is going to start with 0, which is we've never seen any returns from this state. So what every visit Monte Carlo does is it samples an episode. So this goes up to some time step t, ti. And this has to be finite, but it could, be different on different episodes. And then we compute the discounted sum of rewards for that episode. Okay, so starting at time step t, how much reward do we get till the end of the episode? And then for every time step until the end, we see this is the first time that state's been visited. Then we update the total number of times we visited this state for the first time per in each episode. We increment the total return, and we average. So it just like steps along, and it just says, okay, maybe the first time I reached, if you think of the Mars rover example, let's see if I have it in the next one. No, I think I put it. So for a lot of today, I've moved a lot of the worked examples till the end of the slides, but if you want to go through them later, I encourage you to. So for example, in the case of the Mars rover, you might imagine you start in state like S3, and then on that particular one, you get a reward of 1 for that episode. And so then you would average in 1, starting in that state S3 till the end. So this is first visit Monte Carlo evaluation, which means you only update a state at most once in each episode. So if you had something like this, S1 went to S2, went to S3, went to S2, went to S3. So in this case, ... You would update S1 once in this trajectory, and you would update S2 once and S3 once, even though you in fact visit those states multiple times. You only update them for the first time you visit. Yeah.
So could this have the problem where if the state is really rare or uncommon, then we get a really bad estimate, or we just never visit it at all?
So if you don't ever visit a state under the policy, that's okay, because then you don't have a value for it, but then it's kind of undefined because you never would reach it. In this case, as it says, if there's a state that's really rare for you to reach inside of your policy, it might take a lot of trajectories in order to get a good estimate of it. So maybe there's some rare side effect of a treatment plan, and it's going to take a lot of trajectories to observe that. And that was one of the challenges with the COVID vaccine, is that, of course, it was a finite number of people. It was a pretty large number, but finite. And some side effects don't show up until you get many more. It's true generally for treatments, even if on average they're totally fine, that you won't see some of those rare side effects until you get an enormous number of trajectories. Now, COVID vaccine certainly had, the benefits there way outweigh side effects, but my point is just to highlight that, depending on how frequently you see the states, it will take you more or less number of total episodes in order to observe. Yeah.
So kind of it doesn't matter that I saw like S2 again or S3 again in this trajectory.
For this algorithm, no. It probably affects the reward still. It's just that you don't use that data. So an alternative is called every visit, where every time you see the state in that trajectory, you update it. And as you might imagine there, let's say you see it's a really long trajectory and you see S2 many times, then you would update for all of those. Okay. So I'm just going to show you sort of 3 common different ones. So this is a worked example you can go through later if you want, which is if you imagine this is the Mars rover, the rewards are on either side, this is the particular trajectory, you can compute the first visit and the every visit Monte Carlo estimates. So both of those are totally reasonable things to do. Perhaps more common is what's known as incremental Monte Carlo. Okay, and this does kind of what you would expect it to do, which is you maintain a running estimate for what is the value under a policy for a particular state, and you smoothly update that as you get more data. So what we would do in this case is you keep track of the number of times you visited that state, and then you weigh your old estimate by the number of times you visit state minus 1 divided by ns, plus your new return you just observed divided by ns. So that's just sort of your way, you're kind of constantly updating your value function for this state as you get more data. And for those of you who have done machine learning, which is probably most of you, this should look pretty familiar. This is kind of like a learning rate. This is your updated value, and this is your old value. And in fact, that's what we're going to see here. Okay, so you can think of this in general. It doesn't have to be 1 over n. It can just be any alpha here. So any sort of like alpha here is just a learning rate. And we're just smoothly updating our estimate of what is the value function for a particular state. And we'll see lots and lots of algorithms like this, similar to part of what you saw in machine learning. The key thing here is the estimates that we're using, which we'll often call sort of, we also might use the word targets often, is we have this estimate here, And then we have our old estimate. So this is, one sample of what is the return starting in this state till the end of the episode. So I think it's helpful to think a little bit about what this looks like pictorially. And this also relates a lot to, we'll see this when we talk about things like AlphaGo. So I think it's helpful to, and it'll look somewhat familiar to you if you've seen things like minimax trees or expecting max trees. Who here has seen expecting max trees before? Okay, so maybe one person. So most people not. So this might be a useful sort of representation. So I think one way to think about this is what we're trying to do is we're trying to think of what the value is starting in a certain state. And we want to take, we know what the action is we're going to take because we've got a fixed policy. So that says we start in this state S, we take this action A. This is prescribed by our policy. So this is pi of S is going to equal A. And then after we do that, because the world might be stochastic, we're going to have a bunch of next states we could reach. So we have probability of S prime given S and A. And what we're trying to do when we do policy evaluation is we're trying to get an expectation over all the potential futures we might end up in by following this policy. And maybe in some cases there's really good patient outcomes, hopefully most of the time, and maybe sometimes there's less good patient outcomes, and we want to do an expectation over all of this. So we can think of that as a tree, as just we start in a state, we take an action, we look at the branching factor of all possible next states, and then we repeat. Excuse me. So if we think of what the policy evaluation diagram is doing, for each state, we know what the next action is we take, and then we branch again in terms of states. So this is like S prime, and this is S double prime. And so we can just think of like kind of this tree of possibilities going out, but we don't have there's no branching on the actions because the actions are fixed by our policy. So then if we go all the way out, and then what we want to do is we want to figure out what the value function is. You can think of this as, an expensive way to do dynamic programming. What you would do is you would take an expectation over the states, and then you would propagate those values back up to the root. And if you don't find this a useful conceptual way to think about it, it's fine. I think it can be helpful to then think about what these different algorithms are doing in terms of approximations. So this is sort of what we would like to do in order to get V pi of S. But we want to do this in a much more computationally efficient way and also sample efficient way. So what Monte Carlo policy evaluation is going to do is it's going to look like that particular equation here. And what it is doing here is it is going to approximate kind of these full expectations by a sample. So in particular, what it's doing here is it's updating the value estimate by using a sample of the return to approximate an expectation. And we do this many times. We average over many such returns. So it's kind of like saying you have this enormous branching tree. You could do an expectation over all of that sort of explicitly up from the roots, or you could just sample many times, and that's also going to approximate the tree. And the more samples you get, the better that's going to be as an approximation of the tree. And this type of ideas has been used in many different types of algorithms. There's some really nice work in the mid-2000s, like by Michael Kearns and others. And then similar ideas were really the foundation that then led to some of the advances of like Monte Carlo tree search, and then that went into AlphaGo. So this is what Monte Carlo tree search is doing. So notice it's not doing any form of bootstrapping. There's no dynamic programming that's going on here. It's just rolling out. And then what we have here is it is using this here as sort of this sample as an approximation. Okay. All right, so that's how Monte Carlo policy evaluation works. One natural question in this case is how good is that estimate? So we're going to see lots of different ways and lots of algorithms for trying to do policy evaluation. And so you might ask like, well, how do I pick among them? Like, what are the properties I should think about? So one pretty basic property that you might want is consistency, which means that as you get more and more data, does your estimate actually converge to the true value of the policy for all the states? And this is something you probably want, in many cases at least, because otherwise it means that even if you had infinite data, your estimate's still going to be wrong. Now, as we start to think about more complicated settings, we might have to sort of be satisfied with this less good objective. But here, for right now, we're hoping we can just write down the value of every state as an entry in a table, that we should be able to get consistency. A second thing we might want is computational efficiency. We'd like this not to be too expensive for us to compute. We'd like us not to require too much memory. And we'd like it to have statistical efficiency, which is essentially, how does the accuracy of the estimate change with the amount of data? And what that means here is more formally, we'd like to know how quickly do these things converge as you get more and more data. And then in reality, we often care about empirical accuracy, just what is our mean squared error for our types of our estimators. So how good is Monte Carlo? Well, let's just first quickly remind ourselves that the bias of an estimator is so if we have an estimator theta, which we're going to be thinking of as our value function approximation, it's going to be the difference between, on average, what our estimator is versus the true value. That's our bias. And the variance of an estimator is the difference between this and its expectation squared, an expectation of that. And the mean squared error is going to be variance plus bias squared. Okay. All right. So generally, we would like an estimator that has low mean squared error, which means we want it to have low or zero bias and low variance. Okay. Something to think about if you're less familiar with these is whether or not, if an estimator is unbiased, is it consistent? It is not necessarily consistent, just so you know. All right. So what we would like here is that asymptotically, the probability that our estimator, so n here is the amount of data we're using to construct that estimator, the probability that as we get an infinite amount of data, that our estimate is different than the true value, by more than epsilon, it has to go to 0. Okay. So we would like it to be consistent. So how does Monte Carlo fare on these sort of properties? Well, first visit is unbiased. So it's an unbiased estimator of the true policy. And by the law of large numbers, as the amount of data you have goes to infinity per state. So, if you have really rare states, you're still going to need a number of samples to estimate them. But as the amount of data you have goes to infinity, you'll converge. So it's consistent and it's unbiased. Okay. Every visit at Monte Carlo is biased. One way to think about that is, in the first case, all your data is IID, independent and identically distributed. In the every visit case, imagine that you visit state S2, and then 4 steps later you visit S2. Well, their returns are going to be correlated because they're both in the same trajectory, so they're not IID anymore. So that's just some intuition for why it might be biased. But it's also consistent, and it often has better mean squared error because you get to use more of your data inside of a single trajectory to do more updates. And then incremental Monte Carlo methods depend on the learning rate, as you might expect. So, see that here? So let's imagine that we are going to have our alpha parameter, which is our learning rate, which is trading off between our new estimate and our old estimate. It can actually change per time step. So just like how you can generally decay your learning rate, you can change your learning rate here. And if your learning rate is such that if you sum up all of its values for a particular state, it goes to infinity, but the square is less than infinity, then you will converge to the true value. So, and again, this is these are pretty common types of criteria we'll see for some of the algorithms we have that sort of under some sort of smoothness guarantees for the learning rates will have some decent properties. Yeah, remind me your name.
Those conditions aren't met, do you definitely not have a guarantee, or are there other conditions that can give you a guarantee, and those are just some of the clues?
Great question. So asking, is it required to have these conditions? These are sufficient. They aren't necessary always. A lot of that will depend on the particular problem domain too, and what the dynamics in the reward is. To my knowledge, I'm not sure if there are other really general conditions like that, but there might be for specific problem classes. It's a good question. Now, one of the problems with this is that generally it's a pretty high variance estimator. So you're kind of getting, certainly with every visit, or sorry, certainly for first visit, Monte Carlo, you're only updating the state at most once per episode, and so it can take a long time. So you can imagine that if you have very different outcomes from the same starting state, so maybe, most of the time you have pretty average outcomes, but maybe 1 in 100 times you have a really bad outcome. It's going to take a long time for that estimator to converge. So in general, this is a pretty high variance estimator, even though it is often unbiased and it is consistent. And then the other big requirement is that it requires episodic settings. So you have to wait till the end of the episode to update your estimate. And for here right now, that might not seem that bad, but when we start getting into control and decision making, you might want to use the data you have already in that episode to change the behavior of the agent. So you can imagine something like if you're doing self-driving cars or something, you're already getting some evidence that the car is not working as expected within a single episode that might be really long. You might want to use that information to change how you're steering, for example. All right, so just to summarize here, what it does is it's not using the Markov process. It's updating your value function estimate using a sample of the return to approximate the expectation. And under some pretty mild conditions, it converges to the true value of the state. And in some cases, it will turn out that even if you actually know the true dynamics model and reward, you might still want to do this. And I think one thing that's useful to think about here is, systems which you think the Markov property might be violated, at least with the features that you'd be using to represent the state. All right, now let's go on to temporal difference learning. And this is, again, sort of related to Q-learning, which we'll get to in the next lecture. So Sutton and Bartow, which is a textbook that is an optional one for, is it?
I had a quick question. So if we don't know the rewards model, how do we calculate the rewards for the trajectory?
Great question. So the assumption here is that it's kind of like you either are in a real setting where you can sample these from an oracle, or something in the real world is giving you these. So you may not have an explicit representation for the reward model, but you can get them. So like your customer buys something or they don't, or you have a side effect. So you don't necessarily have a parametric model, but you are getting real rewards. It's a good question. Anybody else have any other questions about Monte Carlo before we go on to temporal difference learning? And I'm going to call it just temporal difference learning now, and then I'll specify that it's actually TD0 for most of what I'm going to talk about. So just specify mostly discuss TD0, and I'll specify what I mean by the 0 shortly. So Sutton and Bartow, which is one of the optional textbooks for the class, says if one had to identify one idea as central and novel to RL, it would undoubtedly be temporal difference learning. And what their point is that it really is it's a way still to construct estimators, both for control and for policy evaluation. And the idea is, if we think back to that tree I showed you, and I'll show you some more, there's going to be a way to combine between the idea of sampling to approximate expectations and bootstrapping to approximate future returns. And we'll see that in a second. It is model-free, meaning you don't need to have a parametric representation of the reward function or the dynamics model. And the nice thing is you can use it in episodic settings or in infinite discounted horizon settings. You just set off your robot, and then it's just going to have to learn to act forever. Okay, and one of the key ideas is that we're going to update our estimates of the value of a state immediately, so I'll put pi here because we're still talking about a policy, after every single tuple of state, action, reward, next state. All right, so let's see how that works. So again, remember, our goal is just to compute the expected discounted sum of rewards for a particular policy. Now let's think back to the Bellman operator. So if we know the MDP models and we have a particular policy, we could write the Bellman operator like that. And what we were doing in incremental every visit Monte Carlo is we were updating the estimate using one sample of the return. And the idea now is to say, well, this was one sample, but maybe we could just maintain, we have access to a value function. Why couldn't we look up, and instead of having what the rewards were starting the state till the end of the trajectory, we observed a particular reward, we got to a particular next state. Why don't we use the value function for that state? So what we're doing in this case is instead of using G, we're plugging in the immediate reward plus gamma times the discounted sum of future rewards using our current estimate of the value function for that next state we reached. And here, the reason, one of the things is that we don't have to wait. We can do this immediately. As soon as we reach S prime. So as soon as we reach S prime, we can, as soon as we see the next state, we can immediately update the value of our current state. So we don't have to wait till the end of the episode. We can use this for infinite horizon problems. Okay. So this is what that looks like. And we're often going to call that the TD target. And again, that should look like machine learning, and it should look like what we just did with Monte Carlo, that what we're plugging in here is we're saying we're taking our old estimate and we are shifting a little bit by our learning rate towards our target, which is our reward, plus our discount sum of future rewards using that plug-in estimate. And when we think of sort of how much our estimate is changing, we often call that the TD0 error, which looks at, how different is my current estimate of the value of a state versus the estimate that I'm plugging in. And again, if you've seen Q-learning before, this is going to look really similar to what we had, but there's no max or things like that. You'll see those soon. Okay. So the TD0 learning algorithm just looks like the following. You sample a tuple of a state action rewards next state, you update the value for that starting state, and you repeat. And so your T goes to T plus 1, and then you get the next tuple. You just do this over and over and over again. So like in our Mars rover example, you have sort of state action reward next state, you update, and then you just shift along. Let's see what that might look like here. So in this case, let's imagine we have a policy where we always take action A1. We're going to make our discount factor 1 to make the math easy. And we're going to assume that any action from state 1 or S7 terminates the episode. And then what we see in this case is we have the following trajectory. We start in state S3, we take action A1, we get a reward of 0. So this is the reward. We transition to state S2, and so forth till the end of the episode. So what we would have in this case is that we would make it so that the first update we would do would be V of S3. And what we would say is that's my old estimate of V of S3 times 1 minus alpha. I've just rewritten the above equation here because this was basically 1 and this is alpha times minus V, plus alpha times the immediate reward plus gamma times V of S2. Okay. So that's what that would look like. And here, imagine that I've initialized all of them to be 0 to start. So this would still just look like 0. Okay. And in fact, what would be the only state I would update to not be 0 in this episode? For it to be updated, not to be 0, either its immediate reward has to be 1, or it has to be transitioning to a state whose value is not 0. Yeah, so what we're seeing here is that in this case, we have state action reward next state, and so this is the TD update. And what I was saying here is that we've initialized all of them to be 0, which means that in order for their value to change from being 0, either their immediate reward has to be non-zero, or we have to transition to a state whose value is not 0, because all of them, their current value is 0. Yeah, okay. Were you going to guess which state it's updated?
Yeah.
Which one?
It was, when you're in state state 1, you have a reward 1.
That's right. Yeah, so this is, so none, you don't see any reward here until you get to state S1. I'll just highlight it here. So at that point is when you update your value function. That's the first time that you get to anything that any reward becomes non-zero. So in that case, what you get is S1 is equal to V of S1, 1 minus alpha, plus alpha times 1 plus gamma V of S terminal. S terminal is always 0. So it just becomes alpha times 1. So why am I making do a lot of algebra here? I want to do it because if you work this out, and I won't go through it here, but I think it's a useful exercise, the TD estimate you would get for your whole value function at the end of this episode is quite different than what you get with Monte Carlo. So TD updates after every single tuple, every single state, action, reward, next state tuple. And so that means when you reach the end of the episode, if you look at what your value function would be, and I've written the value function here as just as a vector, but this is the value of S1, this is the value of S7. So I've just written it as a vector. This is what your value function would be. It would say, oh, my current estimate for S1 is 1, and everything else is 0. But if you look at first visit Monte Carlo, it's quite different. Okay, and if we make gamma equal to 1 here, which I said it would be 1, 1, 1, 0, 0, 0, 0. Why is this? Because Monte Carlo waits till the end of the episode, and then it uses the returns to update any state that was visited once in that episode. And the reason that's important is that now actually we filled in a lot more things, because we observed in that case that not just did we get a reward here, but then we saw what S2 got, which was also a reward of 1, and what S3 got, which was also a reward of 1. And the reason I bring this up is that there's going to be different choices about how these behave, particularly when you don't have a lot of data at the beginning, which may be more or less data efficient or sample efficient. And the ideas of sample efficiency will come up a lot. We'll see that a lot later on, but we'll see it on Thursday as well. All right, so what does this look like in terms of the tree? So we go back to our tree, which is like expanding out potential futures. What we can see here is that TD is updating the value estimate using a sample of ST plus 1 to approximate an expectation. So in reality, if you're doing dynamic programming, you would want to do a weighted expectation over all the next states you could reach, weighted by the probability of getting there. What TD is doing is it's just sampling one of those. And that sample is, an approximation of that expectation. So we're going from this to sampling the next state. But similar to dynamic programming, it is then bootstrapping. So unlike Monte Carlo, which goes all the way out to get a sample of that value function, here we're just plugging in V. So this part looks the same. So TD does both sampling to approximate expectations, and it bootstraps by using your existing estimate of the value function. All right, so let's just do a check your understanding. So this is a poll. So what I'd like you to think about is how this learning rate might affect things. So whether different choices of this is going to weigh the TD target or more or less than the pass V estimate. And what might happen when your state space is stochastic, meaning that when you start in one state, you might end up in multiple next states. What does that mean about convergence and the implication for learning rates? As well as thinking about deterministic Markov decision processes. Deterministic Markov decision processes, what I mean by that is that, P of S prime given SA is equal to 1 for exactly 1 S prime, meaning that there's no stochasticity. When you're in a state in action, you always go to one particular next state. So that's a deterministic Markov decision process. So just take a few minutes now and look into this. And you should be able to select all that are true, but if you can't, let me know. You could not? Okay. Right. Well, then, I mean, again, these are only for your thoughts, so just try to write down for yourself which of these you think are true, and then we'll talk about it in a second. I'll check into these for next time. Yes, that's what I just heard. Sorry about that. So I'll try to fix that for next time. Just try to have in your head of which ones you think are correct, and I'll ask you to compare with someone in a second. Thanks for letting me know. All right, turn to your neighbor and check, and particularly focus on the last two. And see if you agree on your answers for those.
Let's say the MVP has a single state, so if you set think of other
Wait, are you thinking that's true or true?
Yeah, I didn't use it to trivial.
Yeah,
Yeah.
can you just accept
If the reward is zero, it converts to
Okay, so I think that's true. Yeah.
If the value like say like if you're the same string or something. If two states.
No,
I'm gonna make a as soon as when I have like 3 hours just like one I have the truth cost
You can like construct a pretty trivial one for like
that's true.
Yeah, I think like some people had it bad. I didn't have it bad.
No, it's not like it's something.
Didn't have any like so like I think otherwise our past which I think
All right, great. I had some great discussions. Okay, so for the first one, this is going to be false because if we have alpha equals 0, then we don't care about the TD target at all. Just totally drops out. So we never update. In the second case, this is true because this means if alpha is equal to 1, then this part and this part cancels out. We just have this. So that means whenever we see an update, we always update. We totally change our estimate, potentially. The third one is a little bit subtle. This is true. Does somebody want to give me an example where this might occur?
Yeah. If you have like two states where they just keep pointing at each other, is that the case for this one?
Yes, and in particular, if there's if you could go to either of those states with some probability. Yeah. So if you're in these sort of cases, so imagine that like I sometimes think of it as like a coin flip. So imagine that you have one state where after this you either go to a state, maybe it's 50% probability you get +1 and 50% probability you get -1. And then your problem just resets. So imagine it's like a really short problem. You start off, you get 0 reward, you transition to a state, and then your episode resets. So in this case, either on that round, you're going to get +1 or you're going to get -1. So you either get +1 or -1 here, and so you'll just flip back and forth between the +1, -1, +1, -1, +1, -1. So that's just to highlight that if you do have systems which are stochastic, the fact that in your target you are using a single sample of that stochasticity to approximate the expectation can be bad. But that does not mean, and I guess this gets to, I think, was it like that was asking before, that like in many of these cases, it's sort of there's this sort of cases where like it might be possible that this would happen, but it won't always. So in this case, there do exist deterministic systems where even if alpha is equal to 1, you can converge. So again, think of something that I like often to think about really small MDPs to get some intuition for this. If you have a case where there's just a terminal state and there's no more transitions, so like you get to some point where you always go to some terminal state and that it's +10 there, there's no more updates, then just +10. There's no more expectation. And in general, any case where, if there's no stochasticity and you're near the end and there's no more stochasticity in that episode, those can be cases where you'll still converge. Okay, great. So this is just, and I encourage you to go through some of the worked examples if you want to, just to see some more comparisons over, the difference between Monte Carlo and TD methods in this case. Just to summarize what we're doing in TD learning, we are bootstrapping and sampling. We're sampling to approximate our expectation over all the stochasticity. We're bootstrapping because we don't want to use a full return. We are instead taking V to approximate that. It can be used in episodic or infinite horizon settings. It is generally lower variance. We're doing lots and lots and lots of updates. It is a consistent estimator if your learning rate alpha satisfies the same conditions specified for incremental Monte Carlo policy evaluation. I here today only introduced TD0. What TD0 refers to is you take the immediate reward and then you immediately bootstrap and plug in the value of the next state. So we did R plus we did R plus gamma V of S prime. Versus summing up all your discounted rewards for the whole episode. In general, you could have something kind of in between. So you could have plus RT plus 1 plus gamma squared. So you could have something like this. So in general, you could say, like, do some sort of combination of like using partial returns and then bootstrapping. There's a lot of different TD methods that kind of interpolate between taking one step and then plugging in the value versus only plugging, not using any value function approximation. And if you want to think about this graphically, it's kind of like thinking about, do you plug in v of s prime here, or do you plug it in, you know, way lower? Yeah.
Is there like
It's
is there an empirical like estimate of what like a good trade-off for like computational complexity versus performance? Like, have they found like a good number for it?
Good question. Unfortunately, in many cases, it will be depending on the domain. One thing I think to think about here too is that you can think of this part doesn't require the Markov assumption, right? So if you have a system where you're not confident, but maybe you're like, well, maybe it's like, I'm willing to say that I'll plug in a Markov assumption eventually because it's going to be lower variance, but I want to preserve the fact that maybe it's not Markov and sort of have a short horizon. Often people do use something in between the two. So they often do consider this in between for multiple reasons, but it gives you some of this flexibility. It often is a lower bias. It's a great question. All right, what we're going to do now is think about also how some of these ideas relate to dynamic programming, which is what we saw in an earlier lecture, because we could use this also for policy evaluation. We know how to use it for policy evaluation if we are given the models, but some of you guys might have been thinking, well, we have data now. If we have data, because we're taking the policy in the environment, couldn't we use that to estimate a reward model, or couldn't we use that to estimate the dynamics model? And that's what's known as certainty equivalence approaches. So the idea here is that you're going to be getting data as you execute this policy, and you can compute a dynamics model from that data. So you could use like a maximum likelihood MDP model. Remember, right now we're in the tabular setting, so we can have a parameter for every single state in action. So we can just count. We can just say, how many times was I in this state, took this action, and transitioned to this next state, divided by the number of times I was in that state in action. And so this just gives you a maximum likelihood estimate of the dynamics model, and you can do the same thing for the reward model. And of course, as you might imagine, you can do this with much more complicated function approximators, like deep neural networks too. But the idea is that once you have this model, and it's called a certainty equivalence model, because we're now going to ignore any error in these models. So we have finite data. These models will definitely be wrong, but let's ignore that for now. So once you have this maximum likelihood MDP model, you can just compute the value of a policy using the same methods we saw last week, because you have a dynamics model now and a reward model. And you can see some examples about this at the end of the lecture slides. So one of the benefits of this, and this gets to the question, is this is really data efficient. So I showed you an example for the Mars rover before, where we only updated one of the states with TD learning. We updated 3 of the states with Monte Carlo. What this does here is it tries to update, it computes a dynamics model reward model for all states and actions, and then it tries to update all of them. Okay, so it's going to compute a value for every single state. Now, the downside of that is that now we're doing policy evaluation with a full model, which is either going to be something like S squared A for iterative methods, or maybe even worse. So it's computationally expensive, but it's really data efficient. Because as soon as you reach any state for which you get, say, a positive reward, you can kind of propagate that to any other state that you know is possible to reach from there. It's still consistent. It's going to converge to the right thing for Markov models. And it can easily generally be used for all policy evaluation, which we're going to get into. Yeah?
Sorry, what is NSA in this equation?
Sorry, great question. NSA here is the number of times we've been in that state and taken that action.
Okay.
Yeah, so this is counts. Okay, yeah.
This seems like pretty similar to Monte Carlo. Is it? I think so. It's just the difference that you're generating like a probability as opposed to like calculating G.
Great question. We're going to hold that thought for time. It's asking how similar is this to Monte Carlo or not. It's actually going to be pretty different. We're going to see this in a second. We are using our data similar to Monte Carlo. We're using the data we're going to use the data here to compute models and then propagate information, but they're going to end up making some interesting different decisions. So let's see that now. It's a great precursor. Okay. So now let's get into batch policy evaluation. So I've said there are these different methods, they might have different computational complexity, they might be more or less data efficient. So one thing that you might imagine doing, and we'll see this a lot shortly, a lot more next time, is, well, if I have some data, how could I best use the data that I have? And this comes up a lot in the research that me and my lab do, because we're often dealing with patient data or student data or legal data or others where it's really expensive to get the data, or it's costly or it could be harmful, and we want to get as much information as we can out of the data we have. So when I say batch, what I mean is imagine that you have a set of K episodes, and now what you want to do is you want to do policy evaluation just with that data. So what we're going to do is repeatedly sample one of the episodes that we have of those K, and we're going to apply Monte Carlo or TD0 to that episode. We're just going to do that over and over and over and over again. And we'll see this a lot more next time as well. And so the idea is to just understand if we do this, given that finite amount of data, what will Monte Carlo and TD0 converge to in terms of the evaluation of the policy? So let's go through that. There's this really nice example from Sutton and Bardo to kind of illustrate this. We have a really small domain. We have two states. We're going to say gamma is equal to 1. There's no discounting. And we have 8 episodes of experience. So in one episode, we started in state A. We got a reward of 0. We transitioned to B, and we got another reward of 0. Okay. So in this case, you can think of it as like this. You get a trajectory like that. In some episodes, we started in state B, and we just got an immediate reward of 1. And we observed that 6 times. So in 6 trajectories, we just happened to start in state B and we got a reward of 1. And then in one trajectory, we started in state B and we got a reward of 0. So first, imagine if you ran TD updates over this data an infinite amount of time. What do you think the estimate of VB would be? So remember what it works for there is we have 1 minus alpha times our old estimate. So I'll just put V plus alpha times our immediate reward plus gamma times the next state, but here it's just terminal because we always terminate. After B, we always terminate, so you never get any future discounted rewards in this case. So what the updates look like for TD learning is that you would have 1 minus alpha times your old estimate plus alpha times whatever reward you get in B. And imagine you just iterate over these over and over and over again. Does somebody have any guesses of what the reward would be for V of B?
Would it be 0.75?
Yeah, does somebody else want to explain why it's 0.75? I see some nods. Yeah, because in this case, we had 8 episodes. In 2 of them, when we started in B, we got 0. And in 6 of them, we got 1. So we just average those rewards. And imagine, we're just doing this many times. So eventually, you would just converge to this estimate being 0.75. What about for Monte Carlo? So let's do Monte Carlo for V of B. What would that look like? So remember, for Monte Carlo, it would be 1 minus alpha times V of B plus alpha times G, where you start in state B. Is it going to be the same thing? Is it going to be different? So Monte Carlo, we're averaging over all the returns we get starting in that state.
Is it like, so when we start at B, so then wouldn't it be 6/7?
6/8.
Oh, 6/8 again.
Yeah.
But don't we start at A in the first one?
In one episode we start an A, but we're just trying to compute the value of B right now. We'll get to A in a second. Yeah.
Okay.
You're thinking ahead. Yeah. So the Monte Carlo estimate, so we're just trying to contrast, so just to recap, what we're trying to do here is we're trying to see, will these two algorithms converge to the same thing or not? We're going to start off and look at what the value would be of state B. In TD, we would converge to 0.75 because the immediate reward is either 1 or 0, and the discounted sum of future rewards is 0 because we terminate. And in Monte Carlo, we just average over all the returns we get when we've started in B, and that is also 6 divided by 8. All right, so now this is the hard one. Okay, what about V of A? What will we converge to in these two cases? So let's do check your understanding, and you can respond in the poll. And feel free to talk to someone next to you. And again, the intent of this is to think about, are these actually computing the same thing or not in this case? And remember, this is a different setting than I told you before that both of these things can be consistent, but that was if you get infinite data. What this is looking at is if you only have a finite amount of data, and you just go over it over and over again, either with Monte Carlo updates or with TD, will you converge to the same thing? And if you're not sure or you're confused, feel free to put that in the poll too. There's lots of different answers here. So this is a great one to talk to somebody nearby you. So why don't you see if you're getting the same things and can use our collective intelligence. Okay, I'm hearing a lot of good discussion, so I'm sorry to interrupt, but this is kind of a fun one. So why don't we, let's start with TD. So someone want to explain why it's 0.75 for TD? There were multiple people that got that. Yeah, do you want to explain what you and your partner are saying?
Yeah, so I think if you just like look, so we're just looking at like this
And
one.
Remind me your name. Sorry.
Yeah, there's like this one episode where we're at A, and so in that episode, the immediate reward is 0, but then we have to do plus gamma times the reward of the next state B, and then V pi of B is 0.75. We got in the previous part, so just the values to 0.75.
That's right. So Monte Carlo is not that estimate. So TD gives you 0.75. What does Monte Carlo give you? It's not 0.75. And again, multiple of you guys got it correct.
Oh, sorry. I just have a question. Is gamma the same as alpha here?
Oh, good question. No, here I'm assuming that gamma is 1, and it's a great question. So someone else was asking this too. So I'm assuming that alpha is set correctly for these to converge.
Oh.
Yeah, it's a good question. I'm sorry, someone else had that too. So I'm assuming that we're going over our data an infinite amount of time, but we're decaying alpha correctly as we do that. It's a good question. Somebody want to explain what Monte Carlo is? It's not 0.75. Is it?
Let me 0.
Yes, it is. That's great. Someone want to explain why it's 0? So Monte Carlo is 0. Yeah.
So we've only seen one trajectory where A shows up and that is reward 0.
That's right. And remind me your name. Yeah, so what I said is exactly right. So we've only seen one trajectory, and I know some other people made the same observation. So we've only seen one trajectory where there was A at all. For Monte Carlo, we just average over all the returns we've seen so that's only 0. So I bring this up because even though asymptotically, all of these things converge to the right thing under some mild assumptions, with finite data, which is what we're almost always going to have in reality, even if you go over it multiple times, they're converging to sometimes totally different things. And here is what they're converging to in general. Monte Carlo is converging to the minimum mean squared error with respect to the observed returns. So it's just going to set it so it minimizes the error between the observed returns it's seen and its value. So in this case, that would be V of A equals 0. So that is the minimum mean squared error. TD0 converges to the dynamic programming policy for the MDP with a maximum likelihood model estimates. So you guys remember how we just talked about certainty equivalence? What we were doing here is we're taking all our data. The answer you get from TD0, if you do this batch process, is the same as if you had computed your maximum likelihood Markov decision process from the data you have, and then you did dynamic programming with it. Okay? So that will be exactly the same as this. And so in particular, it is leveraging and using the Markov assumption. And that's why it could actually chain these things together. So you could see here, for Monte Carlo, it doesn't know that the value of A has to be related to the value of B in terms of this bootstrapping relationship. But TD is making that explicit. It's using the Markov decision process to say the value of A has to exactly be equal to the immediate reward you get in A plus gamma times the states that I could get into, which is always B, so the value of B. So TD learning is explicitly baking that into the solution you get, whereas Monte Carlo is not. Monte Carlo is just trying to minimize the mean squared error for the returns you see. So they can end up giving you very different solutions, and depending on whether your Markov property is really satisfied or not, you might want one or the other. Awesome. So this just summarized quickly sort of some of the different properties and approaches, and just highlights here that temporal difference really does exploit this Markov structure. And that could be really helpful if you want to leverage that to get better estimates of earlier states, like in the case we just saw. So just to summarize, we finished going through policy evaluation with tabular settings. And then on Wednesday, what we're going to do is talk about control, and we'll start to talk about function approximation as well. All right, thanks. See you then.